All right, we're back. Thanks for watching. Thanks for sticking around if you're still here. Um, we're back, and last time we made a lot of progress because we. Let's take a recap of the diagram, but we made a lot of progress because we fixed the data for good, and we also fixed the training because of that. And we didn't even actually use the exact model architecture from the paper. So what I finally want to get back to is pre-commit hooks and typing, logging. So a lot of the clean coding stuff, because now the data seems to work, but we also need to get to the inverse problems and the sampling. So why don't we do it this way? Let's get right into it. So now that we fixed the training, we can actually remove let's keep the data wrong around. Maybe it'll be useful. But first thing I'd like to do is why don't we do it this way? Why don't we track the loss exponentially then? All right. So trailing loss will be loss if step 0, else trailing loss times 0.99 plus loss times 0.01. Okay. So we just want to loss item. I would like to trail and then every time the loss verbose hits, we'll compute the validation loss. Okay. And we'll print it. Okay, print it here. Except we're gonna print the trailing loss so that it goes down smoother. And that way we can compare with our original paper. We can also print with, I believe it's with what? 2 decimals are enough. Is this not how it is? Is it the other way around? 2F? Yeah, I think it's like this. Okay. Same for this one. So we can only print with 2 decimals. We don't need all that other stuff. Now, also periodically, we can say if step +1 is config train verbose, sampling verbose, then we can only sample here. We can plot the data that we sampled and some print statistics. So at step is recon MSC. Oh, this is what we removed, right? Oh, yeah, I remember now. So recon MSC, I should not have removed that, but it's fine. So this is validation recon MSC actually, which is a pretty powerful metric. I wonder what it was. So it was NMSC. Because we want this to be exactly like the paper. Actually, you know what? This shouldn't be like this because it's dependent on the... Let me simplify this a bit. Let's just sample data. The problem is to sample data, I still need an alpha parameter, right? So I need a step size. There it is, CFG sampling. And CFG sampling has an alpha. In our paper, we use 10 to the minus 11. So let me just do that. Okay, so this should clean it up a bit. Yeah, it wants me to initialize. Okay, so it doesn't, I can't guard against this. So it's 0.0. This should fix it. Okay. So step starts from 0. If step is 0, it starts from the loss. Now, if I train again on, let's say, 50,000 steps, but I say I also want to sample synthetic data every 2,000 steps, but I want to print the loss every 50 steps. No, every 100 steps is fine. This should be it now. If I run torch train, and I have to early stop here. Interesting. Yeah, producing synthetic data may not be that easy. Is there some overfitting happening too? Probably not. Well, this one definitely doesn't work because I turned it off. I may need to read one of my other papers. Nah. Did I say? Because here, this is where I produce synthetic channels. Gamma T0. The heck is gamma T? Oh yeah, beta 1, so neutral beta, yep. I see, so I just do this thingy here. And where the heck is eta T? Oh, we said eta T as in Song and Irma in 2020. So I have to read the improved techniques again, I think. I wonder how I chose that thing and if it was grid search. Interesting. Let's see, how do we pick the step size, which is called alpha here? It is called alpha. Choosing noise scales. No, not noise scales. Noise scales we know how to do. We did that. This is the one. Configuring a Neil engine dynamics. Wow. So gamma is the sigma decay, and alpha is epsilon times this one. Select an alpha that makes equation 4 maximally close to 1. Select an epsilon. So alpha is oh shit. So it's alpha sigma I squared. Oh, wait a second. Okay. But this is equivalent to alpha 0. I'm starting to remember now. So we need to pick an alpha that's variable. How much is sigma 0 squared? Okay. Yeah, this doesn't, obviously this won't work. So the loss is going down exactly like it should. It's probably already settled. So we have models now. Okay, we gotta think carefully about this. So alpha 0. Let me run a console here because I think we can do this actually. So UV run Python. Okay, so we have the max sigma is 3915. Okay. Sigma 0 is sigma L times 0995 to the power of 2310. Good. Sigma 0 divided by sigma L. This is where the 10 to minus 11 comes from. There we go. So is it 10 to minus 10? Square. 8 times 10 to the minus 11. This is if I pick epsilon equals 1. This is alpha 0 if I pick epsilon 1. I'm not supposed to pick epsilon 1. So alpha 0 is exactly this with epsilon 1, but I'm not supposed to pick epsilon 1. I'm supposed to pick select an epsilon. Am I supposed to change the epsilon every... Oh, no. This is a constant, right? This doesn't depend on the step size. What is T? Capital T? Oh, the number of sampling step per noise scale. So this is 1 then, right? Yeah, so my epsilon is fried if it's 2 times 10 to the minus 5. Wow. I feel like I'm doing something bad here. Sigma L is the maximum noise level, right? It is not. Is it? Oh no, sigma L, I got the formula wrong then. Oh, I see. So epsilon needs to dampen this significantly then. Ah, shit, I got the formula completely in reverse. So sigma L, sigma 0 is 39, or I should say sigma 1 is 3915. Let's just implement the formula then. Why don't we do it this way then? Why don't we write code then instead of messing around? All right, so let's see. Define, we want a function that gives us compute epsilon. And it's gonna take as input, what does he say here? T, sigma L, and the gamma, which is the ratio. It's a decreasing ratio, so gamma is less than 1. And that's it. Okay, so we need like this. We need a T, which is an integer, gamma. Well, actually, let's call gamma how we call it then. How do we call gamma? We call it noise step factor, which is a float. And how do we call T? Oh, num steps inner. Okay, good. And what's the third one? The min noise level float. Okay, alrighty. So we're just gonna have to grid search or line search for epsilon. Well, cost function. Let's define the cost of as a function of epsilon, which is a float and returns a float. And this returns a float. Maybe we can actually use a proper optimization thing here. So the cost will be what? Well, we have to implement this whole sausage now. Okay, so let's do denominator is, we can just implement this by hand, right? Oh, shit. So it says min noise level squared minus min noise level squared times, this is the same, right? Yeah. What does it want? 1 minus epsilon divided by min noise level squared, everything squared. Whoops. Okay. And he wants this everything squared. Right? Yes. 1 minus epsilon divided by squared. Okay. Oh, actually, the fraction is the same. It's 2 epsilon then. Oh, actually, wait. We can do this easier then. So ratio is epsilon this, okay? So denominator becomes 1 minus ratio squared. Fraction becomes 2 epsilon divided by denominator. So 2 times epsilon divided by denominator. We're almost there. We have the fraction. Okay, and then we can just return cost. Cost value will be, we can just calculate it now. So it's 1 minus ratio to the power of 2 times num steps inner times min noise level squared minus fraction plus fraction on the outside. Return value. Okay, so it doesn't look too bad. Let me see. Is there a... Is there a way I can search for in Python? Is this guy still training? Yeah, this training is still going very well. So we definitely got it right. Oh yeah, shit, I forgot to check data normalization. Okay, so let me see. So NumPy optimization. Does NumPy have an optimization for minimizing objective functions? Do I have scipy here? Local minimization of scale, not local. I want global though. Global. Minimize the function over a given range by brute force. This is probably what we want. Uses the brute force. At each point, the function is whatever delta of the first vectorized is inefficient because it increases exponentially. We don't care about exponential. NS, what is NS? Number of grid points. No, but I have to do it myself. I don't want this. What the heck is Bazin hopping? Oh, come on. Can I not, like, find the fucking thing here? Okay, I think I'm just gonna do my, should I just do my own, f of x, slice range. This program uses to create a grid of points. Note 2. I think I'm just going to use this scipy optimized brute. Let's start with this one. So do I have import scipy? Yes. Scipy.optimize.brute. Okay, we have it. So then what does it give me? Whoops, sorry. How do I call this? Okay, define f1, f3. Okay. Result brute. What the heck is this, dude? F. Oh, I see. So result brute 0, 1. 0 is the minimum. Okay. All right. So let's put it this way then. So we just need result is scipy.optimize brute. But the cost, like he says, should be absolute of 1 minus value. So we want to find something that's closest to 1. But also, what does he say? Like, how did he say it? So select an epsilon that makes equation 4 maximally close to 1. I don't know what that means. Like maximally. Maximally close? like close, but also higher than 1? I don't know. I'm just gonna import scipy. So then we can just minimize cost. And what else does he want here? I have to say NS, right? Oh shit, I have to guess a range. Each component of the range is tuple. So what, I give it a tuple of tuples? Yes, it's a tuple of tuples. Okay, so problem is I have to guess the min-max values though. 10 to the minus 9 and 1. No, this is too bad. 6 and 3? 7 and 3? And I'm gonna give it a crap ton of stuff. So NS 100,000. Result. Let me see what this does. So I can do from MIMO.sampling import compute epsilon. Okay, I can. So num steps in, or we're gonna have 1. I guess. Noise step factor. We're gonna have 0.995. Did I forget to use gamma in the formula? Oh shit, I did. It's gamma squared. Ach. I made a mistake here. It's gamma squared. Whew, okay. Almost messed that up. So UV run Python again from MIMO sampling import compute epsilon. Okay, how is the model training going? Pretty well, I would guess. Yeah, pretty well. Like it's basically converged down to 120. Yep, this is exactly like the paper. So we're doing very good here. We just need to sample from it. Come on, we can do it. So num steps in are 1. Noise step factor 0.995. Did I get this right, or is this greater than 1? So sigma 1. I think I got this wrong. Wait, hang on. So technique 2. Which one is bigger, sigma 1 or sigma 2? Sigma 1. So then this is also sigma 1 divided by sigma 2. Oh my god, it's the reverse. Okay, so it's 1 over what we call noise step factor. Gotta be very careful here because it's greater than 1. Again, we'll just run this again. Num steps inner is 1 and min noise level, I'm just gonna make this up, we don't really care about it, 003 it was, right? Something like that, yeah. So then from MIMO.sampling, import compute epsilon. Noise step factor, min noise level. Okay, so we're stopped here. So now why the heck does this does not work? Let's see. Does it want me to do just this? Nope, it does not want me to do that. What the heck does it want me to do then? Like, slice between... Oh, I know what it wants me to do. Like, comma here for a tuple, right? Okay, there we go, yeah. All right, so let's see. So result 0. 1.25 times 10 to the minus 9. This is what? The minimum. Oh, so epsilon, I'm actually very capped then. This is not good. Wait a second, so is epsilon that narrow? So if I do cost of result of 1, cost of result of 0. But how come 125 10 to minus 9, it's out of bounds though? Like, what is even happening here? I guess it makes sense. So my epsilon, oh, I see. I'm way undershooting the epsilon here. I know what's happening. I'm overshooting it. So I think I'm way off here. If I go 10 to the minus 13 to 8. Result 0. Here's the epsilon. Okay. All right. Yeah, okay. So epsilon is about 9 times 10 to the minus 10. So then I go 9 times 10 to the minus 10 times... What was my alpha 0? 39.15 divided by 0.003 squared. Is my alpha really this much? 15? What am I trying to say here? Something is wrong then. Am I sampling the wrong way? Because... Okay, so then I know how to fix this. 10 to the minus 11, 10 to the minus 8 tuple. Result of 0 will be the value. But okay, this is all nice and good. But what am I trying to say here? Because if I... So how do I sample from the score here? Something is fishy, right? So I have my alpha step. And my alpha, this is my epsilon. Damn it. Is this what I call epsilon? Is it what I call alpha 0 then? But it's not my epsilon because I do current sigma divided by... Yes, it is my epsilon. Yeah. So in the start, this is gigantic. Yeah, this is the right formula. So this is alpha 0. I know the confusion. And I call alpha 0... What do I call... What is my alpha 0? I think I know what I did here. I made a mistake. Times R to the outer step. Yes, I made a mistake. Alpha 0 is 15 for me. Because then, once this reaches the end, finally, this has to be it. Okay, so alpha 0 is actually... Because then I just take alpha, and it's 2 alpha plus alpha, right? So then I have step size, 2 times step size, and step size. Okay, finally, yes, okay. So what I call alpha 0 should really be... I mean, sure, we can use this value, right? 9 e minus 10. But it's also times... what is this? Times... I know what this is. It's 1 over the noise step factor to the power of noise levels minus 1. So this will be ginormous for me. It will be 15, right? Because, so let's test this out. So it'll be 9 e minus 10 times 1 over 0.995 to the power of 2310. Squared even. Sorry, so to the power of 2 times 2310. Yeah. To the power of 2. Damn, because I have to square it too. Is this what I do here? Yes, I do square it. Yep. Yeah. So current sigma. Yeah, the first sigma is huge. Sigma end is very small. This is exactly this formula. Then this one gets decayed. Very careful here. One more mistake. It gets decayed by r squared times at every step. Oh my god, this is very sensitive here. Because r itself measures the sigma ratio, which is called gamma in the paper. All right. Yes, so I have to decay it by gamma squared. And it actually says that in the paper. Where the heck is the progression? Come on, it's gotta say it here. So where is, what am I looking for? Am I insane? No, I'm not insane. It's squared. Yes. Yeah, it's squared. Yeah, so it's times gamma squared. So every time you get the gamma squared. I mean, I'm surprised he doesn't have a formula. Then it's just like gamma squared to the power of whatever. Gamma times 2 to the power of whatever. I think this is it. Okay, so a crap ton of fixes now. Okay, so then yeah, training is going well. I'm confident. Yeah, training is going perfect. All right, so it's actually going down to 100, exactly like the paper. Yeah, we have this. Okay, so I fixed the sampling. All right, let's take a break and we'll implement the sampling using the save model. This is gonna be it. All right, thanks for sticking around. We can cut one more episode here, but yeah, training's going great. We finally figured out the formula exactly, and we actually implemented something exact. I think we got this. All right, thanks for sticking around. See you after.